UN 영어뉴스. How the moon is making days longer on Earth. Billions years ago, the average Earth day lasted less than 13 hours, and it is continuing to lengthen. The reason lies in the relationship between the moon and our oceans. Throughout human history, the moon has been an inextricable, ghostly presence above the earth. Its gentle gravitational tug sets the rhythm of the tides, while its pale light illuminates the nocturnal nuptials of many species. Entire civilizations have set their calendars by it, as it has waxed and waned, and some animals, such as dung beetles, use sunlight reflecting off the moon's surface to help them navigate. More crucially, the moon may have helped to create the conditions that make life on our planet possible, according to some theories, and may even have helped to kickstart life on Earth in the first place. Its eccentric orbit around our planet is thought to also play a role in some of the important weather systems that dominate our lives today. But the moon is also slipping from our grasp as it performs its finely balanced astro ballet around the earth, circling but never pirouetting, which is why we only ever see one side of the moon. It is gradually drifting away from our planet in a process known as lunar recession by firing lasers of reflectors placed on the lunar surface by the astronauts of the Apollo missions. Scientists have recently been able to measure with pinpoint accuracy just how fast the moon is retreating. They have confirmed that the moon is edging away at a rate of 1.5 inches every year, and as it does so, our days are getting ever so slightly longer. It's all about tides, says David Walton, a professor of geophysics at Royal Holloway, University of London, who studies the relationship between the moon and the earth. The tidal drag on the earth slows its rotation down, and the moon gains that energy as angular momentum. The gravitational tug of the moon on the earth's oceans creates the tides, which in turn drag the moon into higher orbit. Essentially, as the earth rotates, the gravity of the moon orbiting above tugs on the oceans to create high and low tides. These tides, in fact, are a bulge of water that extends in an elliptical shape both towards and away from the gravity of the moon. But the earth spins on its axis much faster than the moon orbits above, meaning friction from the ocean basins moving beneath also acts to drag the water along with it. This means the bulge moves slightly ahead of the moon in its orbit, which attempts to pull it backwards. This slowly saps our planet's rotational energy, slowing its spin while the moon gains energy, causing it to move into a higher orbit. This incremental braking on our planet's spin means that the length of an average Earth day has increased by about 1.09 milliseconds per century since the late 1600s, according to the latest analysis. Other estimates put the figure a little higher at 1.78 milliseconds per century. By drawing on more ancient observations of eclipses. While none of this sounds like much over the course of the Earth's 4.5 billion year history, it all adds up to a profound change. The moon is thought to have formed in the first 50 million years or so after the birth of the solar system. The most widely accepted theory is that a collision between the embryonic Earth and another object about the size of Mars, known as Theia, cleaved off a chunk of material and debris that coalesced into what we now call the moon. What is clear from geological data preserved in bands of rock on Earth is that the moon was a lot closer to Earth in the past than it is today. The moon currently sits 384,400 kilometers from us on Earth, but one recent study suggests that around 3.2 billion years ago, just as the tectonic plates were starting to move around and ocean-dwelling microorganisms were gobbling up nitrogen, the moon was just 270,000 kilometers from Earth, or about 70% of its current distance. The faster rotating Earth shortened the length of the day, so that within a 24-hour period there were 2 sunrises and 2 sunsets, not just one each as today, said Tom Uhlenfeld, a geophysicist who led the study at Friedrich Schiller University, Jena, in Germany. This may have reduced the temperature difference between day and night, and may have affected the biochemistry of photosynthetic organisms. What studies like his reveal, however, is that the rate of lunar recession hasn't been constant either. It has sped up and slowed down over time. One study by Vanina Lopez de Azarevich, a geologist at the National University of Salta in Argentina, suggests that around 550 to 625 million years ago, the moon would have been retreating as much as 2.8 inches a year. The speed with which the moon was moving away from Earth definitely changed over time, and will do so in the future, says Uhlenfeld. For much of its history, however, the moon has been moving away at a far slower rate than it is currently. The enigmatic far side of the moon. In fact, we are currently living in a period when the rate of recession is unusually high. The moon would only have had to recede at its current rate for 1.5 billion years to reach its present position, but the process has been occurring since the moon formed 4.5 billion years ago, so it was clearly much slower at points in the past. The tidal drag right now is 3 times bigger than we might expect, says Walter. The reason may be due to the size of the Atlantic Ocean. The current configuration of the continents means that the basin of the North Atlantic Ocean happens to have exactly right proportions to generate a resonance effect, so the water it contains sloshes back and forth at a rate close to that of the tides. This means the tides are larger than they otherwise would be. As Walton puts it, think of pushing a child on a swing. They get higher if each push is timed with the existing motion. If the North Atlantic was slightly wider or narrower, this wouldn't happen, says Walton. The models seem to show that if you go back a few million years, the tidal strength drops right off because the continents were in different positions. But it is likely to continue to change in the future. Modeling predicts a new tidal resonance will appear 150 million years from now, and then will vanish around 250 million years from now as a new supercontinent forms. The Next Giant Leap. This article is part of The Next Giant Leap, a series by BBC Future. It charts humanity's return to the moon and beyond, answering some of the big unanswered questions about our nearest neighbors in the solar system. Along the way, you might like to read other articles related to the series. Artemis record-breaking mission, how the UAE got to Mars, the hunt for trees sent to the moon. So, could we eventually have a future where the Earth no longer has a moon? Even at its high current rate of retreat, the moon is unlikely to ever leave the Earth entirely. The sun's own calamitous demise will probably intervene long before that happens in around 5 to 10 billion years. Humanity is likely to have been snuffed out long before then. In the shorter term, however, humanity may itself play a role in lengthening the days a little further by reducing the amount of water locked up in glaciers and the ice caps due to melting caused by climate change. The ice basically suppresses the tides, says Walter, noting that around 600 to 900 million years ago, when our planet is thought to have entered a particularly frosty period known as Snowball Earth, there was a dramatic slowdown in the rate of lunar retreat. The impact is, however, hard to predict, as some of this will be counteracted by rebounding land masses as the weight of ice sheets is lifted from them. and other complications. In theory, the next crop of astronauts to fly to the moon with NASA's Artemis program may be able to say they looked back at their home planet from further away than their predecessors on the Apollo program 60 years ago, although the point they arrive during the moon's elliptical orbit around the Earth will probably determine this more. The distance between its closest and furthest points varies by 43,000 km every 29 days. For the rest of us, our lives are far too brief to notice the picoseconds being added to each passing day's length. If you blink, you will miss it.